Welcome. Good morning, good very early morning for those who in the other time zones. And I'm really impressed. A lot of nations that joined from different continents.
And it's already late in Asia.
Okay, so the topic that we choose today is net capacitance. And this mainly, I think we need to introduce ourselves. So yeah. Günther starts first, he's the oldest one.
Not so much older than you. So I'm Günther. I'm engineering manager at KK Prime. And we do mainly act as a design house. We do the development of electronic stuff, and we support our customers like KEMET, where Axel is.
Good, that's me.
Working, yeah.
Okay, I think it was a handover to me. So my name is Axel Schmidt. I'm, as Florian and Günther already mentioned, I'm working for KEMET Electronics. Recently now bought from a Taiwanese company. So KEMET is now based in Taiwan. But I mean, for the next 2-3 years, nothing really changed. Still KEMET, still the same products and still the same people you are dealing with. My position is Senior Technical Marketing Manager. That means I'm interested also a little bit about the ecosystem that our products live in. And that was more or less the starting point. So I'm based in Munich area in Rosenheim. And I'm also in charge of all the semiconductor companies like Infineon, Texas Instruments, Analog Device, Microchip, etc., etc. And from there to there, we exchange information. So they need all of our products. And we, of course, they're part of the ecosystem that our products are in. So I'm always interested in how the parts works in the application. That's basically my stuff. And so what I see, the trend is going to higher switching frequencies, so the lower ripple voltages. And so the question is that sometimes the capacitor behaves a little bit different than probably you'll see in a data sheet in a catalog. And then the question is, so why and how can we measure that? And can we, how do you get the net capacitance? I'm dealing most with customers in automotive area. And so the major method or outcome of that is definitely it's about cost. And so the question is, how can I cost optimize my design? And our approach is that you minimize the number of components to that. And what you see here in the picture is the one demo board with a typical output voltages, so 1.0 volt, 1.2, 1.8, 3.3, the typical voltage that you need to supply these semiconductor parts. And on the left side, you see probably the switching frequency. It's going to higher and higher switching frequencies. And the question is, how do the parts behave in the application, not only in the data sheet?
And the parts get smaller and smaller.
The parts get smaller and smaller.
Yeah, that's what we faced with our customers.
So I think more or less all new designs are working with switch mode power supplies, and the OMICRON gives a lot of application notes and information about the stability. And one part of the stability of this open loop and closed loop system is, of course, the capacitance and the ESR of the capacitor. And so what we give you is in a data sheet some information that's probably not applied to your application parameters at the end of the day. And the question is, if you look on not only on KEMET website, also on other websites, we give you a bunch of information, but the question is, how do they fit together? How do you manage that? So you see on the bottom of the screen the graphs from one of our competitors. And what you see is you get the impedance, you get S parameters, you get DC bias characteristics, you get AC voltages, and you get temperature characteristics. But now you have this 5, let's say 4 different information. And the question is, how do they fit together? How do you manage that? So how is the net capacitance, the real capacitance that's in your circuit? And what's typically doing is that you superimpose all these different effects. So what we have is, we have a nominal capacitance, And then we have, of course, the manufacturing tolerance. That is something you can choose by your order code. In ceramic chips, it's typically 5, 10, and 20%. But the majority definitely is a 10%. Then, of course, there's a certain impact of the temperature of the component. For X7R, it's per definition plus minus 15%. So these two effects are somehow easy to understand. But then the next two, DC bias and AC ripple, that are more tricky because there's no standard that applies here. So that means the loss of capacitance when you apply a DC voltage is not defined anywhere. So you get some information from the suppliers, but it could be really, it's a huge variation from 20% to 90%. And recently what more and more pop up is the AC ripple has also a certain impact. That means if you apply the ripple current on the output of your regulator, then it drops an additional percentage and has also a certain impact on the stability of your closed loop system. Then the other one is frequency and aging. So we skipped that for that presentation. I mean, I cannot do everything in this 30 minutes here. So we focused on these two effects, DC bias and AC ripple mainly. So if you look on a KEMET data sheet or catalog, so then you see how we measure capacitance. And that actually is based on an international standard that's called EIA 198 that defines how we measure the capacitance. And first of all, it's no DC bias in there. That's the first step you need to note. And the second one is that we have two different combinations depending on the capacitance. For the majority of the parts, which are less equal than 10 microfarad, we measure at 1 kilohertz plus minus 50 hertz, and then the AC voltage on top, or how we measure, is 1.0 plus minus 0.2 volt RMS. And for bigger components, simply because of the impedance and the current capability of the components, we switch down to 120 hertz plus minus 10 hertz and 0.5 volt as the AC amplitude, and then the tolerance would be plus minus or 1 volt in addition to that. So as you probably know from the regulator 2 slides earlier, 500 millivolt or 1 volt ripple on a 3.3 or 2.3 or 5 volt system is way too high. That's nobody can live with. And the question is, so what happens if the ripple is only 25 millivolt, 100 millivolt as the typical application values?
And with DC bias.
And the DC bias, of course. So nearly all major players here in the market have some kind of information in the meantime. So you see here on the x-axis is the bias voltage, and on the y-axis you see the capacitance change for a certain component. And we choose here for 1 mic 6.3 volt. And you see with the typical 3.3 volt for the 6.3 volt component, the loss is about minus 35.5% loss. That means that leads into, from the 1 microfarad, it's left over 650 nanofarad. But is, this is actually measured at 1 kilohertz and 1 volt RMS. And the question is now, your system is running at 3.3 volt, and the ripple is only about 25, 50, or 100 millivolt. And the question is, how does this affect the capacitance and all the others, following the sequences out of that? One thing in general to the stress in the component, actually it's depending on the dielectric thickness. So you see on the left upper corner, it's cut out of MLCC multi-layer ceramic chip, and you see that the layers are like a comb structure, and in between, of course, you have your dielectric material. So, and all these effects, the AC as well as the DC, at the end of the day, applies on the electric force on charged particles within that material. And this force on this charged particles depends somehow from the electric field. And the electric field is defined by the applied voltage and the distance between the electrode, which is the dielectric thickness. So that means if we change the dielectric thickness, and that is what actually happened. If you look on the upper right formula, so if I have a 1 microfarad capacitor, nearly the same voltage range, and coming from 0805, 0603 and going down to 0402, the only way I have is to change my dielectric thickness, that increase, of course, the capacitance, and I can stack more layers inside the smaller area that I have. So that's the way all manufacturers are putting more capacitance or higher capacitance value into smaller case sizes. But if you do that and you thin out the dielectric thickness, so you increase the effect. And that means smaller components, same cap values, typically have a worse DC bias than bigger components like 0805, 1206, or 1210. So we have some hints about this, how do you measure the capacitance? Actually, that is one we published some years ago, and it's about the measurement itself and the correct measurement. So we all know that the equipment has a certain source impedance, which is typically 50 ohm, like in the Bode 100, and then you have your device under test. And what actually happens is that there's a voltage divider between the source impedance of your device in the Bode 100 and the capacitor. So, and this, of course, the voltage split up, and I come to that a little bit more in detail in the next slide. But this measurement here, what you see on this Agilent or Keysight or whatever they're named right now, is actually done at 1 kilohertz, which is not your application switching frequency. And that was the question that we are digged into, and we are really curious about what happens really in your circuit. So because at least I was not so familiar with all this, dB, dBm things and the real voltage, and I know that you can kill the Bode 100 with too high voltage. So that is simply the levels we are dealing with. So the Bode can handle from -30, which is 7 millivolt, up to give me the right one, up to 13 dBm, which is 1 volt. And then you see we have DC bias voltages above that. So we need to take care about in the measurement that we don't apply too much voltage on the Bode 100. And then you will see later in the slides that we have to have more power to apply the right voltage to the component. And that's the reason why Florian sent us nicely the amplifier. So we can have an additional 12 dBm add to that, so we can come up.
Yeah.
So we can, so 25 dBm, which relates to 4 volt RMS, which gives you the 12 volt peak. And that's the formula in case you are not have that present right now. So
that's how we started.
So that's the idea we had when we have, during the lockdown. So we meet here in the office. We have once a week an official meeting with some beers, and then we let some ideas flowing. And that is the outcome of one of them. And now I will hand over to Günther to explain a little bit what the thought about that.
Yeah, when Axel approached me at that time, the first time to say, okay, we need to measure the behavior of the capacitor while it's on DC bias, we faced the first problem that the amplifier or everything is measured with a 50 ohm resistor here, and the capacitor changes its impedance, and while doing that, there is less and less AC ripple on that capacitor. This forces to limit our measurement frequency range, so it goes down. The next question was, how can we apply the DC voltage on that? What is the standard? What are the formulas and so on? We go into the details. So a typical measurement, a one-port measurement on the Bode 100 is connecting the output on the device under test. This time it's a capacitor. So we have a capacitor under test. Now we apply DC voltage on the other side and bring that point from the AC down to ground with a large base capacitor. So that ratio should be 1/100 to have good measurements. The next thing is, and you have to take care to have also a discharging capacitor on this side to avoid that the charging is not done through the Bode 100. Setting up everything with the on the software as a one-port measurement, and you are done. So
now this was the more formal approach, and then so how we start. And I was really impressed about Günther's capability to do hand soldering. So actually, what you see here is,
by the way, this small one is a capacitor.
So, yeah, I think you see. So we had this resistor, discharge resistor. We have the base capacitance, and then you have the device under test, which in our case is this 0.0421 microfarad capacitor. And you see here, it's a really small part, so it's really soldered to the middle pin of the SMA connector, and then he really hand soldered it to I think it was 22 microfarad something capacitor, or 100 microfarad capacitor in that case.
Yeah.
And then we did some first trials just to see how it works, and it looks pretty good. So
yeah, and well, as that was good for a first test. We had to do also something for further and more details and repeatable test, and having the capability to test also various capacitors. So we needed a PCB, and that PCB, well, from the schematic you see it's the connection to the Bode 100, this time also quite close. These are the various capacitors we could place in on this position, so that we have the capacitor on the test, not only 0402 or 306, 805. All that is possible. The same as you have seen on the picture before, the connection from on the base side from the capacitor on the test to these capacitors needs to be close and robust, and so to give this capacitor a good ground or a good AC ground while we charge it through the DC side with some DC bias, and they are also spaced in equal length so that they don't get any kind of parasitic resonance. Discharging resistor so that when you switch off the power supply, it's also discharged these capacitors, and a large elko for what we had in our drawer. And unfortunately, it was not from Axel.
It's not from us, which I apologize.
But it works with everything. And that was then the first results. When we started to apply a DC voltage on the capacitor, the capacitance drops. That means the impedance of that capacitor increases. And you can see that here, with increasing the voltage, there is also the capacity going down and the impedance going up. Another thing is also that the self-resonance frequency you see here is moving up in the frequency as well. However, and that's only got from experts, above the self-resonance frequency in this area, you don't see any impact of the DC bias. That means in this frequency range above the self-resonance frequency, it's mainly the ESL and the ESR dominating the behavior of the capacitor. And as the ESL depends on the number of layers on the mechanical setup, this does not change with voltage.
So one remark from my side. I mean, okay, it's an OMICRON lab event, but I really give my respect to the software. I mean, you can really. It took a while. I figured out, how can I einblend and fade in the different cursors at different frequencies and different measurement. I think it's really everything what you need. You can do with the software. So I was close to ask about markers, and then I figured out it's already implemented. So it's really, I think the software is, in my mind, is one of the best for dealing with the VNA. I didn't find anything I could improve at the moment. So
yeah,
really
Florian and his
good.
team have done a good job on that. So that's how the capacity over frequency and DC bias behave. Now we come to the next thing, how DC bias and AC ripple correspond to each other. And to measure that was not so easy. So when we as a first thing, the AC voltage, if you do that measurement, which you have seen before, then you see at higher frequencies, the voltage, the AC voltage on that capacitor drops down. Has to be, it's not constant at all. You have to do some compensation measurement. You have to do some measures against that so that you keep your AC voltage constant while you change the frequency. And that's then.
That's a sweep. What you see, I mean, it was a very fancy idea from Günther to really record an oscillogram as a whole sweep. And what you see here really is actually the voltage across the device on the test of the capacitor in that case.
So for low frequency, you see high voltage, it drops down till the self-resonance point, and then the impedance goes up of the capacitor, and therefore the voltage at the capacitor goes up as well.
I think we need also to speed up. Let's give it time. Okay, so just to highlight a little bit, I did a short simulation on LT Spice about this effect. So where we have the 50 ohm impedance, and then you have a capacitor and a set, and you clearly see the simulation is more or less in line with what we have already measured in that case. And so you see again, can I measure to move that thing? Okay. I have a window of the data, but you see the cap, and then we have measured at different frequencies. And then you have this 72 ohms, 72 milliohms, and this up to 7 point, the minimum at 1 megahertz is 72 milliohm. And then the voltage across the capacitor. And you see it at 1 megahertz, it drops down to 1 millivolt, which is far away from the standard.
Yeah. Case. And that shows us that we need an amplifier. Oh.
Whoa.
Oh, thank you.
We got the message, Florian.
Okay. So, but another good thing from the Bode 100 team was they already implemented a level compensation curve you can enter, and therefore that's how we did that for the lower frequencies. And we found out quite fast that we need an amplifier. That's how we did then the setup. We got a nice amplifier from Florian to put that and to stress the capacitor under test even more. And with that compensation, we were able then to keep the voltage over the test frequency kind of constant. Nevertheless, you normally have not such small capacitors. You use, as you have seen in the previous picture, large capacitors, 1210 or something like this. And you need always capacitance of 10, 20, 50, 100 microfarads. So we say, okay, how can we make sure that our measurements are for the switched mode power supplies can be translated? And for that, we can say, okay, if we go for a 100 microfarad capacitor at 1 kilohertz, even the amplifier has not enough output power to measure. So we need to substitute the 1210 by an 0402. And the 1210 has round about 20 cubic millimeters, and an 04 has 80 times less that volume. So we said, if we change the volume, we can also change the capacitance. A capacity similar. So we started, instead of having a 100 microfarad 1210 capacitor, using a 2.2 microfarad capacitor at 0402 to say we get similar results. So, yeah.
Actually, this is, I think I did that table to figure out how much
power do we need?
Power do we need to have 1 volt across the capacitor to fulfill the standard measurement thing, or the capacitance in that case.
And you see, at 1 kilohertz, we are in the right range. Even 10 kilohertz with 31 dBm, it's 1 watt. It's way off the amplifier. And if you go in this region, you're already in the kilowatts. No way. So that's in the setup with the amplifier. And we got the signal to speed up. Okay, we put in the amplifier, we go for that setting with external coupler. It's the same thing, and we did the measurement.
Yeah, it's not actually the same thing. I mean, in the previous slide, you see 3.3 volt RMS. Now we have 7 volt RMS, so the 4 volt RMS more. And then.
So that was then the measurement with DC voltage. A lot of curves here, and we made some analysis out of that. And the result is it's on the low AC. It's behaving stable, and if you get a higher AC voltage, the capacitance even increase, but only if you are in an area of DC voltage level coming close to the capacitor specification here. That's 5 volts. Yeah, and with low AC, low DC. You get even a turnaround point. The capacitor drops again. The capacity drops again.
So I mean, it's remarkable that those lower curves, they have monotone increasing behavior, while the curve at 1.8 volt at a certain point it declines. So and that is something. We probably need to do some more investigation on that.
Okay, so that's wrap up. So if you just superimpose the different behaviors of all these given things from the manufacturer, it does not reflect the real behavior of your capacitor in that schematic. Some, like the DC bias and the AC ripple, do even help you in your schematic to not drop the capacitance. It's increasing the capacitance. How much? How's the behavior? It's always a little bit different.
Yeah, just on my side. So getting back to the beginning, so we need to do some more investigation. Again, the approach is that you have a cost optimized design. That means you don't use more of these MLCCs. And I see a lot of design where people more or less spread out MLCCs just to be sure they have enough capacitance. When you deal with automotive customers and they typically count the tenths of a cent, then it really makes a difference if I use 4.7 microfarad or 3 4.7 microfarad. And that actually the targeting, what we want to do is we want to get closer to the real behavior that allows the customer to really not over design their application, just really only need or that number of components they really need for the application and not some safety margin, which probably increase the cost of the overall application on that.
Okay, so while we ready for your questions, we just have some of our test boards left. If you're interested, just let us know and you will get that.
Yeah, I mean, the approach is that if somebody interested in this kind of investigation, we probably can collaborate. I mean, it's not our full-time job, so it's a kind of interesting things that we try to analyze. And if some others out there would like to work with that or collaborate, and then we're definitely happy to work with them together. So that's a major message on this.